Okay, so this is basically nothing new. It's continuation of what we did last time. I'm going to just review what I said last time, which is how do you solve problems involving forces. So first thing is draw FBD. Second, use equations of motion. Free body in this case we only look at F equals ma. So the net external force is mass times acceleration, and the third step is and this is optional, it depends on the question you're going to get, use kinematics, that is A equals dv dt and V equals dr dt to solve for V and R as required. Okay. Now I think the first step is the most crucial one, because if you go wrong in the first step, then you may not get part 2 and part 3 right. So I'll just briefly sort of give you a few examples where you could go wrong, and I'll show you where people go wrong normally. So here are a few examples, and this is not a comprehensive list of examples. Okay, so problem might be draw the free body diagram for that. Draw FPD. We might even ask you a short answer question asking you to draw the free body diagram. So the correct way to draw this free body diagram is to only draw the mass and nothing else. Okay, so if you draw this and then show mg and n and f, this is wrong. Okay, because ground should not be shown. Okay, you could show ground. It's perfectly fine to show the ground. If you show the ground, then you're not allowed to show the normal force and mg, because the ground and when the two interact, then n and mg basically cancel the effect of each other. So yeah, we have to show it wrong. If we have to show a square. Yeah, you can show the square. You can also show a dot. That's fine. Yeah. If you're not comfortable drawing a square, you can draw a dot or something which it's clear that. But in this case, there's no friction. Assume no friction. Unless you're told, don't assume friction. So the right way to draw the free body diagram is to only draw the mass. That's why it's called a free body diagram. You're freeing up bodies. Question?
How would you prefer us to show it? Center, actually the opposite, or at the bottom?
You have to always show it at the point of contact.
Okay.
And the reason is, well, for this particular section where particles can only translate, you can show it anywhere. It will not change anything for you here, because we are only doing sliding motion. When we go to the next chapter, which is on rigid bodies, where we have translation as well as rotations, the point of action of the force actually does matter because it induces rotation. So putting a force at the center is different from putting a force at the contact surface. For this part section, yes, you can draw it anywhere. I ideally want to draw it at the interface. So the right free body diagram is this: F, mg, and because I've pulled off the ground from the block, right? The block cannot just float in the air. It has to be interacting with the ground with some force, because of which it's on the ground and it's not penetrating the ground. So that's why there's a force N.
So for the applied force, do you say we just put F or we put that F applied?
In that case, I've shown it as F, so you want to put F instead of F applied. Okay, so here's that was probably a simple one. Here's another example. Okay, and M2 is greater than M1. I don't think it really matters. It doesn't matter. M2 will move down. So draw FPD, ignore. Not necessary. It's not necessary. You can have a perfectly smooth table and this block will still, M2 will still move down. In real life, yes, there's friction. You cannot eliminate it. But in the world we live in, where textbook problems, we can give you a problem if you say there's no friction, or you can ignore friction. Okay, so there are multiple ways to draw free body diagrams. First of all, you note that there are two masses, and when you have F equals ma, there's an M there. So you want to think of drawing free body diagrams for M1 and M2. So there are really three free body diagrams you can draw. You can draw a free body diagram for M1. Okay. What I'm going to do is I'm going to cut the string or the cable. So when I cut the cable, that cable which is cut interacts with the rest of the cable through a force. So let's call that force tension in the cable. And then there is M1G, and then there is N. Let me call it N1. Yes, we do, in the previous section, yes, we did tension. So the other block is M2, M2G, and there's tension, right? So that's the free body diagram. I've removed all strings. Now it's perfectly fine if there's actually a third free body diagram you can draw, which is involving M1 and M2. So if you want to draw this free body diagram, sometimes it does happen that it's best to draw a free body diagram of the composite system. We call this 1, this 2, 3 would be okay. So now, because the string is intact, it's not being cut anywhere, you should not show the tension force. That's very important, right? The tension force will not appear in the free body diagram. Okay, so in the first two free body diagrams, I cut the string. So when I cut the string, I need to replace the effect of the rest of the string with the tension. Because the tension is changing. Here I've not cut the string. It's intact. That means that tension force should not be shown. Very common mistake. So here, here's this one. Yeah, so I'm getting to that. So the tension will not show up. Now I've pulled the pulley there, and the pulley is actually connected to the table, right? And it cannot be just floating in the air. So you need to put a force at the center of the pulley, because otherwise that pulley cannot be in that position. So I would need to put a force R, and I don't quite know the direction, so I just put it in a random direction. So it needs to be resolved in the x and the y direction. So what you get from this free body diagram is that the tensions don't appear, but you have this thing R, which is an unknown. So if I ask you, for example, find the tension, then you'd probably draw this free body diagram, this free body diagram, write the equation, and solve for tension and acceleration of the car. If, however, I told you to find the reaction force, you can actually draw this free body diagram and figure out the reaction force. So it really depends on what you're after.
So we have to account for R and not control to
Yeah, you wouldn't bother. So if you're normally this one, you never try to find R. Normally try to find tension and acceleration. I'm just trying to show you the various possibilities, various free body diagrams you can draw. Okay, so I think this will be more clear once we start solving problems. So here is the first problem. So if the supplied force is 150 newtons, determine the velocity of the 50 kg block when it has risen 3 meters starting from rest. So this block A rises by 3 meters from rest, and it does so because there's a force of 150 newtons applied as shown. You're going to find the velocity when x equals velocity of A when x A equals 3. Okay, so first thing you want to note is that this looks a lot like the problem we studied in the previous chapters, right? Pulleys. However, the difference is that the point B has a force applied to it. In the previous section, the point B, it was pulled down either with a velocity which is given to you or an acceleration. Right? In this case, it's a force. So once you see a force, you got to start thinking of Newton's laws. Okay. So in this case, I'm going to use kinetics, which is Newton's laws. I have 3 pulleys there and a mass, so I can draw basically 4 free body diagrams, 1 for each pulley. So that is 3 for each pulley and 1 for the massing. So let me start doing that. So let me call this pulley B. Okay, this is force F acting down. Now, one thing which is not given here, and you've got to assume this, is that the pulleys are massless. Okay, we'll see problems where the pulleys have mass later on. When the pulleys are massless, where the string is inextensible, you see that the force is actually transmitted through the pulley. So the force on the left side of the string is the same as the force on the right side. This assumption is only true if the pulley is massless and the string is also massless and inextensible. If those 3 conditions are not met, massless, inextensible, and pulley string doesn't have mass, then that you cannot do that. In this case, you have to draw it a little bit late. You probably don't need a datum line, as you see in a bit. So those forces I got from those 3 assumptions. Now the force which is holding the pulley up should be 2F to balance the forces which I've drawn there, right? So I've sort of already applied Newton's laws in the vertical direction. I have not written the equations, I've already applied it. You see how I've written it as 2F. That is because the sum of forces should be equal to 0. Then I draw the free body diagram for pulley C, and I think it's best to draw it just below B. So there's going to be a force which is equal and opposite to the force up, right? Because I cut the string there. Since the string is inextensible, there will be the same force will act on the other side, and the force acting at C, so this is B, this is C, is going to be 2f, and that comes from, again, applying Newton's laws in the y direction. There's no acceleration. There is an acceleration, but there's no mass. So m times a is 0, because mass is 0. So 2f is the force acting down. Then I draw the free body diagram for pulley. Let's call this pulley A. So this string here is drawn over here. It's going to have a force of 2f that opposes the 2f coming from there up, because it's the same string. And then since this string is inextensible, there will be a force 2f on the other side. Right? Forces are transmitted to the pulley. And then this force here is going to be what? What's this force? 4f. Yeah. And then finally, the mass A has 4f upwards, because coming from the same string, and then there is m a g downwards. Okay, so I sort of applied Newton's laws as I went through them, through each of the pulleys, and I did that because the mass of the pulleys was 0. It's a statics problem in that case. However, I've not applied Newton's laws for the mass m. So I'm going to apply Newton's law now. So this is step 2, Newton's law for MA. So I would choose, well, in this case I think it makes more sense to choose the y direction to be positive downward, because the mass is going to accelerate downwards and not upwards. So applying Newton's laws, net force is mass times acceleration. The net force in the y direction, there's no motion in the x direction, right? So the net force in the y direction is mag, okay, and that's positive, acting downwards. Downwards is positive for me, minus 4f equals mass times acceleration in the y direction. So ay is g minus 4f divided by m. So g is in, this is in SI units. So g is 9.81, f is 150, and mass m is 50. Mm-hmm. Mm-hmm. Okay, so when you do this calculation, you see that AY is actually negative. Right? Because you get 9.81 minus, you get 4 times 3 is 12, so it's minus something 3 points. Okay, which means my assumption was wrong. This system is not going to move down, but it's going to move up. Now if you get this, then what you need to do is, you cannot, maybe I should just write the answer down. Anybody calculated this? It's 12, 9.8 minus 12, I'm going to write this as 9.8. 2.9, 2.9 or 2.2? 19, okay. Okay, so when you see this negative, now I've told you that when you see a negative sign, it just means that it's going to move up and you stop there. Well, that's not the right way to do this problems involving, well, I'll actually do, sorry. So when you get that sign, it just means that it's opposite to what you assume, and that is basically what it is, which is it's not moving down as you assume it's moving up. So you can assume it to move in the way it is moving, and then figure out the answer, and that is your final answer. However, you will see that when you have friction, things become tricky. If there was friction in this problem, and you solve the problem and you get a negative sign, that means things are going to move opposite to what you assume. Then the final answer you get is the wrong answer. You cannot stick that. You cannot use that answer. You have to go back to the problem, reverse the signs, and solve it all over again. And that's reason is because friction force always opposes motion. So if you solve the problem forward and you find a negative answer, opposite to what you assume, that means your force, which you started off with, was the friction force was opposite in the direction of what it should be, and so your calculations are incorrect. So as long as there's no friction, your answers, your signs are right. Your sign, in this case, AY is downward. This is the value. But if there was friction, there's no friction in this case. If there was friction, then you have to go back, reverse your assumptions, and then solve it again.
So if you learn the y-axis, you made it go downward, you actually would have probably what you're saying would have done that.
No, I don't think that's so. If I flip the signs to positive upwards, I would have found that y would come out to be positive. Yeah, but then it depends on how I assume it to move. I would have liked this as minus MA times y. It depends. You can switch this and switch that, and you have the same answer. So you could, let's say you assume it's positive upwards. In this case, it will be 4f minus MAG, and depending on how you assume the y, if you assume that A is going to move down, you still put a negative sign and you get the same thing, you get a contradiction. Okay, so I said only holds true for no friction case. So given the AY, we can find the velocity. So the step 3 is doing the kinematics. So we want to find the velocity when xa is 3 and the velocity at the initial position is 0. So the way you can relate the velocity and position given the acceleration is through the formula v square equals 2ay x minus x0. So initial velocity is, well, final velocity is unknown, initial velocity is 0. Acceleration, I'm going to assume that, okay, let's just assume that, well, it's acting downward is positive, it's acting upward, so I'm going to just keep the sign. But now x, you're told that the block A moves upwards by 3 meters, right? So I need to put negative. Let me just write it as y minus y0. It might be much simpler if I write it this way, so that you don't get confused with the direction. So y is 3, minus 3, and the reason is because in the problem you're given that block A rises up by 3 meters. So since it rises up by 3 meters and my convention is downwards is positive, I need to put a negative sign. The initial value is 0. So if you do this calculation, you get VA square equals, well, VA equals square root of whatever you get from multiplying this, and the answer is 3.62. Yeah. You mean? Yeah, that's fine. Yeah. Yeah, you could also use dv, dy, v dv dy equals ay. You can use this too. Did you use that? Yeah, you can use that. Just that if acceleration is constant, then it's simple. Now, one place where you might want to use the formula which you use always is if f was given as a function of time. So f is constant, right? But if f was 150 times, let's say 150 times y, okay, in which case your acceleration will be g minus 4f, which is a function of y. So the acceleration is not constant, and that's where this formula would be the only way you can solve this problem and not the way I showed you, because acceleration is not constant. That was another common mistake made in the first exam, where people took the uniform acceleration formula, this formula, and they applied to the case when the acceleration was not constant. That's wrong. This is only true when A is a constant.
Where do you use that?
That's a negative sign. Should be here. Sorry, my bad. It should be negative here. Okay, next question. Yeah, I'll post the solution to that. That'll take me some time. I'll just say 8 minutes. A 2-pound collar fits loosely on a smooth shaft. So this is 2 pound. If the spring is unstretched when S is equal to 0, so spring is unstretched. Okay, in that position. And the collar is given a velocity of 15 feet per second as shown here. Determine the velocity of the collar when S equals 1 feet. So we have to find okay, so the problem is initially the spring is vertical. My bad. This is not a problem in the vertical plane. There is no gravity. It's in the horizontal plane. Okay. Now the book doesn't quite. There are problems in the book where they would show a problem like this and then solve it with gravity inside it. They don't quite draw the gravity. In this case, it's really this particular problem. I'm telling you the problem is in the horizontal plane. So gravity does not influence the motion. The gravity acts now to this setup. So the spring is this way, it's unstretched, which means force is 0. Then it's given a velocity of 15 feet per second and marked to the right. Clearly it's going to stretch because it's not with velocity. However, the spring is going to prevent it. The spring tries to, it's going to stretch, but when you stretch a spring, the force increases. So there's going to be a force which prevents the spring from stretching, which means that there's going to be some kind of an acceleration or a deceleration acting there. So we got to find the velocity of C when S equals 1 feet. And clearly this is a problem where we've got to analyze the motion of C due to the effect of a spring, which means that it's a kinetics problem. So I'm going to draw the free body diagram of the collar and try to show all the forces on it. Okay, so physically what I'm doing in the free body diagram is I'm pulling the collar out of the rod and trying to replace the effect of the spring and the rod with forces. So when you stretch the spring produces a force along its length, right? So Fs is along the length of the spring. Okay, I'm going to call this theta. This is theta, which is unknown, but I can find that because I know the dimensions. So, as I said, there's no gravity in this because this setup is in the horizontal plane. So gravity is not there. What other forces do I need to put in this figure? The weight is not there because it's in the horizontal plane. Is that it? Are you sure? So when you have a collar on a rod it's interacting with the rod, with the coil in some way. So there's going to be a normal force. The friction has nothing to do with the normal force. There is a force which is preventing this color from moving in the, I would call that the y direction, right? If there was friction, then the friction force would show up in this direction. So it will show up in this direction, mu times n. But there's no friction in this problem. No, that's not true. We will definitely that. Okay, so that's the free-body diagram. Let me write the equations of motion. Let's call this x in the y direction. So the equation of motion is, well, we need to find the velocity of c, and the velocity of c, we can find the velocity if we know the acceleration in the x direction, where x is the direction I've shown. Right? So we're not quite interested in knowing what happens in the y direction because we have the force n and we're not interested in it. So I'm going to just try to write the force equilibrium in the x direction. So the net force in the x direction is mass times acceleration in the x direction. Okay. You could write Fy too, but all it will do is it will help you to figure out n. So some questions we might actually ask you to find n, in which case you need to write Fy equals mass times Ay. And by the way, Ay is 0, right? Because the color cannot move in the y direction. So let's try to expand this out. Fs acts in the, it's an angle to the vertical, so I'm going to resolve Fs in the x and y. So the only force acting in the x direction is Fs sine theta, and it's got a negative sign. Okay, is there any other force? So nx in the vertical direction, there's no contribution. So if there was friction, yes, there would be a force which you need to add here, but in this case it's just, that's the force. So Fs sine theta is max. This is an unknown. The question is, can I find Fs and sine theta? So for sine theta, I need to use trigonometry. So if this is theta, this angle has to be theta. This is 1 feet. You're given that this is 1 feet. Yeah, my bad. This is 1 feet, but you want to solve it as a function of x. So this is the position of c when it has moved. In general, the motion is at a distance s from the left. So you would write it as a function of s. So I'm going to try to write sine theta as a function of s. So to get sine theta, I'm going to redraw this here. This is 1, this is s. What's this? What's this side? S squared plus 1. So theta, so sine theta is the opposite side, which is this, s divided by s squared plus 1. Okay, so I figured out sine theta. Fs is the spring force. The spring force times S is 1 after after t seconds. You got to write it as a function of s because the force is varying. You got to integrate later on and to get s. So k times the stretch in the spring. I need to find what's the length of the spring. It's basically s squared plus 1, right? This minus the original length of the string. What's the initial length of the string? Of the spring. It's 1 meter, right? This 1 feet equals mass times ax. Oh, my bad. I have to write sine theta too. Sine theta is s divided by so ax is minus k it's negative, right? Negative k Okay, so this is AX. Okay. I know K, I know M. S is the distance from the left. You know the final distance, but you don't know what. Well, you're going to keep it this way. Now, the step which I have to do in order to get the BC, and I don't have time, so I'm just going to write the equation and I'll complete it later on, is you're going to find velocity when S is 1 feet. So you got to use the formula which you talked about earlier, which is V dV ds is equal to AX. And so V dV is AX ds. And the limits of integration are 0 to 1, and V goes from 15 feet to VC, which is unknown. So this AX has to go in here, and you got to integrate it. So in this problem, you cannot use the formula V squared minus V0 squared is 2AX. And the reason is because the force or the acceleration is not constant. Okay? Okay, so I'll complete this, post it, and I'll see you guys on Friday.